Yeah, so as I said, the topic is work, energy, power. And work is similar to the torque that we talked about. So we know that torque, or this weird T that we had, it is equal to force times displacement. And we said that, all right, force and displacement are like that. Now, this produces a turning effect, right? It makes things turn, which means it can either go clockwise or it can go anti-clockwise. Yeah, so as I said that torque can either be clockwise or anti-clockwise, which makes it a vector quantity. Now, there is a different similar formula to what torque is, but this time we'll call it work. And work is force times displacement. Okay. So that is force times displacement. And what this means is that this one is scalar and it doesn't have any direction. Now that may seem quite weird. Now, where exactly is the difference here? So the difference is that torque is when force is perpendicular to displacement, which means that force and displacement have a 90-degree angle between them. If the angle is different, we will take that into account and make sure that only the perpendicular part actually has any effect on whatever you're talking about. Now, as far as work is concerned, force is parallel to displacement. All right. So that's what force and distance or displacement have in relation with each other. Notice that displacement is a vector. So this is a vector, force is a vector, but together when they multiply, they get this. Now, there's something that you'll notice here, that when I multiplied force with displacement, I put a dot in there, right? And here I put a cross. Now, you will study later on in A levels or beyond that multiplication is of two kinds. One multiplication gives us a vector and one multiplication gives us a scalar. The multiplication gives us a scalar, we call it dot. And the multiplication gives us a vector is a cross. In O levels or IGCSE, we don't really concern ourselves with that difference. We just have to remember that work is scalar, it doesn't have any arrow on it, and torque is a vector, and that means it has a direction, and that direction can be clockwise or it can be anti-clockwise. All right. Any questions so far? So does everybody understand what this means? We have two things, same formula, but very different meanings. And the main difference is that in torque, force and displacement are perpendicular, but in work, force and displacement are parallel. All right. So here the idea then comes that if force and displacement are parallel, do things really have to move for that to happen? Or does all movement mean that work will apply? So here, the definition may seem a little counterintuitive. So for example, it's a very common example that you have a book. So this book, you push it on a table. So this is a tabletop. You push this book, it moves from here all the way to here. So the book is over here. It has definitely experienced a force, and that force has caused it to move from here all the way to this point, and that is the displacement. How will I measure that? I'll say, all right, from this corner to this corner, or from middle to this middle point. Wherever I want to look at, I will just measure the displacement that they've covered. And because the displacement is parallel, it's in the same direction as where the force is applying, I'll say that, all right, work is force times displacement. Whatever force was. So let's suppose force was 2 newtons and the displacement was 3 meters. Then my work done would be 2 times 3, and that would be 6 Newton meter. But this time, just to differentiate from torque, I will say that instead of saying Newton meter, I'll say this is joules, named after a scientist, Joule. So 6 joule or joule is what the unit of work is. What does it mean? 6 joules simply means that you have applied maybe a force of 6 newtons and moved the thing 1 meter. Or maybe you have applied force of 1 Newton and moved the thing 6 meters. Or you have applied a force of 3 Newton and moved the thing 2 meters or the other way around. As long as the overall 6 joules is there, that implies that that's what it is. Now, something that had a force of 1 Newton could move with the same work, could move things 6 meters away, because then 1 times 6 is also also 6. So that would also mean 6 joules. So two things with different forces but different displacements can have the same work. And that's very much possible. An important point to note over here is that the mass or weight of the book did not matter. It is irrelevant, because the work done depends on any force that is applied. That is why we also always say that work done by something, by this force or whatever, on a particular object. So that's how we, that's the semantics of this work done thing. All right, so you have the same book, and now you move this book, you apply another force on it. And now you move this book back to this point. Now, has there been some work done? So let's suppose now the force was 3 newtons and the distance again is 3 meters. So that is force times displacement. You are getting 3 times 3, 9 joules work done now. But my question is, has there been an overall work done? So on the left side journey, or the blue one, there is some work done, 9 joules. On the right side journey, there is some work done, that is 6 joules. But overall, the book has come back to where it started from. If you were to look at overall, then the displacement is 0, which means overall work done is 0, because for any force times 0 is 0. So that means that if something comes back to its original point, original space, original position, then the work done is 0 because there is no displacement. That is one way of looking at it. Another important example for this. So let's suppose you had this book, this same book, and now you have this. So there's a student who is carrying this book, okay? And now this student moves from here all the way to over here. So they are now carrying the same book here. So they have traveled a displacement of, let's say, 5 meters. And what they're doing is they're holding the book, and just to hold the book, you know that book has a weight. So let's suppose this weight was 10 newtons. So the student is applying 10 newtons force upwards to cancel that out, right? So that means they have applied a force of 10 newtons on the book so that it's stationary, it doesn't fall down or it doesn't go up or whatever, it is in equilibrium, and they have moved 5 meters. Question is, has the student done any work on the book? Force is not parallel to the displacement. Yes, that is true. The force is upwards and the displacement is towards the right. So that's a 90-degree thing. So that means no work done, because the force that is parallel to this, so the parallel force is 0. There is no parallel force. So even if it travels 5 meters or 500 meters, the work done is 0 because there is no work done by the force that is parallel to the displacement. So that's something that you have to consider whenever you're solving questions on this, that you will only consider the force that is parallel and parallel to the displacement that any object has covered. So that's it. We have seen what work is. How does that translate to energy? And what exactly is energy? The concept of energy is something that we all have to some abstract sense. It's a very common part of our active vocabulary. We all use this word one way or another, that that person is very energetic or agile, okay? Or you know about the energy crisis that many countries, including ours, has experienced. And you also know that, all right, energy is something that you need and you get it from food. And we also talk about that, oh, energy makes things move, or all the most pollutant companies, they are in the energy sector, or the most powerful or even the most like highly paid and highly profitable businesses are in the energy sector. So what exactly is this energy thing? So in physics, although there may be many different definitions of this, In physics, we say that energy is the capacity to do work. It is the capacity to do work. And what work? The work that we just defined. So what exactly is work? Work is the effect that force has on something. Force makes things move. We know that. Newton's second law, F equals ma. It makes them move, and how much distance it makes them move compared to the force that they've applied. That is one way of looking at what work is. So energy is how much something can make things move in one way. So that's one way of looking at it. That how much work can something experience because of that energy. So energy is something that is inherent to things, and it is the capacity. It is the capacity. It's the caliber. It's the ability that something has to do work. It does not mean that they actually have to. They can, and that's important, that they can do this work, but they don't actually have to. And turns out energy is something that we can either apply, and when you apply energy, you do work. So for example, if there is the same book, for example, and somebody took it from over here, moved it, I don't know, put it on a bookshelf that was 2 meters high. So now the book is in this bookshelf. So somebody has picked it up, placed it over there. So they have done some work on it because they applied a force that was upward, and they moved the distance that was also upward. So now they have put it there. But interestingly, when you do that, you apply energy and you do the work on something, and that thing can store energy. So energy can be applied or it can be stored. So some stores are easier to transfer to one another. So for example, there is a store of energy that this book now has just because it's at a higher distance from the earth. We say that this has a potential energy, and that potential energy is the energy stored in it. So this book is now an energy store. It has potential energy in it. I'll get to the intricate details of what potential energy is. Similarly, if you took this book and you started running for whatever reason, then you will have a store of energy in you, and that would be kinetic energy because you're moving. So kinetic comes from the Greek word for movement. So kinetic energy is the energy in something that is stored in it just because it's moving. So by the time it stops moving, that store is depleted. It just goes away. Similarly, things that are hot, they store thermal energy in them. Now, this does not mean that that store is always going to be there or it's permanent. It can go away the moment its situation changes. So thermal energy is a store of energy. There is another more permanent sense of storing energy. We call that is chemical energy, that it is more permanent than the other one. Similarly, there's the internal energy of things that already they have this. Similarly, there is the nuclear energy, which is more permanently or more securely stored in stuff compared to others. So there's another energy that is electrical. That is again in a particular situation that thing is there, that thing has the energy in it and is supplying it, or it may be just doing the work. So the four on the left one are only there for the moment circumstances support them being there. And those on the right one are more permanent in the sense of being stored. But all of these can be transferred. Interestingly, energy is the currency of physical world. You can use it to do work. So that's like spending energy. So all of these energies, regardless of what form they can all be spent to do some work. Or by doing some work, you can store some of that energy. That's also possible, the other way around. But interestingly, all of these can neither be created nor destroyed. I know that that's a cliche. So energy is something that is conserved. So energy is a conserved quantity, which means you cannot create it, you cannot destroy it. So the energy that is there in the world, it has been there since the beginning of time, and there is no way we can so far increase or decrease it. If we found that would mean that our understanding of physics will be radically changed, like extremely radically. We will have shake the foundations of the physics that we understand, or even chemistry or any other science that we have. So this idea that energy is neither created nor destroyed is foundational to modern science. But what you can do is that you can take any of these forms and convert it to any of the other one. And that process will require some technology. People didn't know that. What did people know? So initially, people knew that, all right, if I started moving and I took some logs and I pushed them with that, then that could be something that I maybe move that log up to a hill. So what was that person doing? They were moving, they were taking the kinetic energy that they had and converting it to potential. But where did they get the kinetic energy from? From their muscles. And they were moving. So where did the muscles get their energy from? From the chemical energy in the food that they had. But where did the chemical energy in the food come from? It came from the sunlight that had light energy in it. Okay, so that was the light energy that sunlight had. So sunlight gave it to the plants, plants converted it to chemical energy, one way or another, in one food form or another. It came to the person, and the person had enjoyed that food or whatever, and then they started running with that weight and they converted to kinetic energy. And that kinetic energy, they took some weights, they moved it to a particular height, and they changed it to potential energy, and that is when they stored it. And turns out, even 5,000 years after that, we still see that energy stored in the Pyramid of Giza. So all those pyramids, they were built by people who were taking the light energy of the sun, converted to chemical energy of the food, converted to kinetic energy that they had in their body or in their muscles, converted to potential energy of those stones, of those pieces, and then they placed those pieces up on some other stones and all that, and converted it to a pyramid. And that's a marvel of the world. Similarly, I'm talking to you like this. Where is this energy coming from? So the cycle over here is that right now, I have sound energy that I produce because I have vocal cords, and those vocal cords get their energy again from chemical energy. So they convert it to sound. Where does chemical energy come from? From sunlight. And now that sound gets transferred to my laptop as electrical energy. And that electrical energy is transferred all the way across the world, wherever you are, to you, usually into either light energy or just as electrical signals, depending on what medium of communication we have. And then that is then converted to, again, sound energy. And then you can easily hear that. So that's the cycle of energy that we have here. You can pick anything that gets some work done, any activity that involves some work done, and you can find these energy connections in there. All right, so let's try to do it for, I don't know, I have, okay, so I get a call on my phone. So I hear a ringtone. What's the energy cycle over there? So yeah, you're right. The ringtone is sound energy, and that sound energy, let's work out backwards. So sound energy was produced by the speaker in my phone after it received some electrical signal from the phone. But where did the electrical signal generate from? Where did the electrical energy in the phone came from? From the chemical energy. Okay, what chemical energy? Yeah, battery. Battery or cell has a chemical reaction happening in it. There's the anode, there's the cathode, it's transferring charge, it's doing some work on the electrons that move from one place to another, from the negative terminal to the positive terminal. And that is some chemical energy that's coming from. Of course, that is coming from bond breaking and bond making and all that, but we'll get to that in chemistry. So there's chemical energy in the battery. So battery is a store, a more permanent store of energy. And you will notice that every store that we talk about is on the right side, and every finite store or a momentarily store that we have is on the left side. So that chemical energy in the battery obviously came from the electrical energy. Interestingly, where did that electrical energy came from? It came from a power plant. Now, it depends what fuel that power plant was running on. So the fuel, so for example, if that was a thermal power plant, then what it was doing was that it was using some fuel, it was burning it, which also had chemical energy, and it was burning it to produce electrical energy. And that electrical energy was transferred all the way to my home, which I used electrical energy. I converted it to chemical energy in the battery, and that then obviously rang the bell that I had. But where did that fuel get its energy from? The chemical energy in the fuel. So you can see that we have this cycle here: electrical energy in the phone, chemical energy in the battery, back to electrical energy in the house, back to chemical energy in the fuel at the power plant. And then where did that fuel get its chemical energy from? Yes, Ahmed, you're absolutely right. So where did the fuel get its energy from? Let's suppose we are the richest country in the world, Pakistan, because we are the only country that affords to burn fossil fuels to produce electricity. We actually use furnace oil. Even US cannot afford to burn furnace oil to produce electricity, but we do, because either we are too rich or, I don't know, ignorant. So yeah, we are burning fossil fuels, and that fossil fuel obviously had its energy stored in it as chemical energy, and that came from some animals that lived millions of years ago, animals or plants. Sure. Where did they get their energy from? When they died, they had chemical energy stored in them. Where did they get it from? I'm sorry, I'm missing a connection here. Dinosaurs got the energy from the sun. I don't see that. Like, were dinosaurs capable of photosynthesis or something? Yeah, the connection in there is plants. So the dinosaurs that ate other dinosaurs or directly enjoyed plants, both of them got their energy from the plants, and those plants stored energy as chemical energy. So do you see that? Chemical energy in the plant consumed by the animal or the whatever plant itself, and then that got stored in the form of oil and all that. So again, it all came from the sunlight. And turns out most cycles of energy will all take you to sunlight. Most of them. Sure, there are some of them like geothermal energy. It comes from the volcanic activity that we have going on under the crust of the earth. But again, you can also argue that earth came from a cloud that was created because of the sun. So it all comes back to the stars, which are the major source of energy. Our solar system has sun. There may be other solar systems or other systems that have that energy. So yeah, I'm sorry, Ahmed, I don't know that word. What does that mean? Compsognathus. What are those things? Feel free to unmute yourself. I would like to know that. It's a small dinosaur. Oh, so fossil fuel was made from smaller dinosaurs.
नहीं सर मैं कह रहा हूँ कि आपने पूछा था बड़े डायनासोर्स को मतलब कि उनकी क्या डाइट थी सर तो मैं वो बता रहा था कि smaller dinosaurs or plants.
Yeah, so you will notice that most of these cycles will take you to wherever you start from. Wherever you start from, you take any activity that you do. You're doing cycling. You can argue that cycling, the energy that you're supplying comes from sun. Yeah, and it actually does. Some forms of energy only exist because of the activity that they're doing. So wires have electricity transferring in them. So they have electrical energy that the electrons are carrying. The moment there is a power shutdown, that electrical energy converts into something else, which is usually thermal. Similarly, there is light energy. So there is sunlight that's right now coming to me. So that is sunlight. In some parts of the world, it's not coming from there. It's probably coming from some artificial sources of light like bulbs or tube lights or LED lights or whatever. They also have electrical energy converted to light. When you start a car, you have fossil fuel that had chemical energy converted to all these sound, light, electrical signals, and obviously eventually the kinetic and maybe potential energy of the car that you are in. So all of those conversions keep on happening. Unfortunately, every conversion that you do, every single conversion that you do reduces the energy that is useful. And that's an important concept here. The usefulness, useful energy. Now, we know that energy is a conserved quantity, so you cannot destroy it, which means that technically you will never be wasting any energy because it's impossible to do that. But we can still say that some activities are wasteful. Why? Because we spend a lot of resources, in fact, a lot of energy to harness the energy that we have so that we can do some work. And then let's suppose I took some petrol that had 400 joules of energy in it. But my car, because it's a pretty old one, 3 years or 4 years old one, so that does not have a very efficient, so that's the word, efficient engine. So maybe it just converted only 100 joules of it to something that I can actually use, the kinetic and all that. But rest of it, the 300 joule thing, the remaining 300 was converted to heat or thermal energy. This 100 joules out of it, it converted 10 to sound and 90 to kinetic. So the purpose of actually using a car is to move from one place to another, at least for me. And then that only requires kinetic energy. So I just want my car to have kinetic energy. But the petrol that I had, it had 400 joules, but the car eventually moved because of 90. And interestingly, that 90 was also wasted because the road that I was traveling on, maybe 30 was used to work against friction because of the friction of the road. So 30 out of that was used to actually overcome the friction. So my car could actually move. And then it just moved because of 60 joules. And I'm like, bhag nahi rahi. Because the energy that it has is 60 joules and the energy that I gave it was 400. And compared to that, if you notice that the 100% that I gave it was 400 joules, but what I actually got was only 60 joules. So I can either do the cross multiplication or I can just use the formula that this energy or this machine that I have is only 15% efficient. So the efficiency of this thing is 15%. What does it mean? Every 100 joules that you give it, 85 of those will be wasted. Now, what does it mean to be wasted? It means mere kaam nahi aa rahi. Whoever is doing that work, uska purpose ke kaam nahi aa rahi. That's all. That's what useful energy is. Useful energy is the energy converted to what purpose you wanted it to be. So I want my car to move. So my purpose is to move. My purpose is to have kinetic energy. Any other form that I have will be wasteful for me, whether it's heat, whether it is light, whether it is sound. I don't want that in my car. I just want it to move. So what do? We try to make machines more and more efficient. It's impossible to have a 100% efficient machine because you can never really convert friction to zero. It's always going to be there wherever there is something moving, wherever there are moving parts. friction is going to be there. It's a contact force. Similarly, when you drive a car, you have air resistance, which is also a form of friction. You also have these braking things, and you have to brake, and that increases the friction and all that. So there's always some energy wasted. But as engineers, if some of you were to go into this power production sector and all that, your job will be to design and implement ways to make sure that less energy is wasted. Why? Again, number one, it wastes money, time, resources that were put into making that system over there. That system was designed to do a particular task. If it's not doing that, then it is wasting the energy that it has. All right. So again, energy is never truly wasted. It's just converted to a form that is not useful to you. And that is what wasting energy is. Energy is always going to be in one of these forms, or maybe some other forms that are not written over here. But regardless of what happens, it will always be ability to do work. And once you apply that energy to do work, that is when it has truly served its purpose. And you decide what you want it to work on. Do you want it to run a fan? Do you want it to run a power plant? Do you want it to, I don't know, run a laptop, or move stuff from one place to another, or take things to take people to 100-story high building? It all depends on what work you want to get out of it. And that is where you apply the energy. The moment you stop that means आपने साइकिल तोड़ दिया, तो एनर्जी आपके काम नहीं आएगी, वेस्ट हो जाएगी, थर्मल में कन्वर्ट हो जाएगी usually. There are two forms in here that are combined to call them. So these two, we combine them to call mechanical energy. Similarly, what is internal? It is the mechanical energy of particles that make anything up. So particles, you know, are in constant random motion. That is kinetic particle theory. So their kinetic energy, their potential energy comes from their constant collisions with each other. They have forces in them that are pulling them together. So they'll try to overcome those. So that form is all internal energy. So that you increase that, and that will increase the heat of that thing, which is then simply the thermal energy of stuff. So as you can see, any form can be converted to any other form. And what do power plants or chargers or these kind of things do? They turn them from the left-hand side stuff to the right-hand side stuff. Generators and all that. They try to convert energy from one form to another, and it depends what purpose it is serving. You want a charger, you are trying to store energy, which means you are trying to convert it to a more permanent form. You want some other motor or something, you are trying to convert it to a form that is more useful. So that is what these machines, all of them do. And it's a big, big sector, the power sector. Okay. And we'll now talk about what power is, but we will actually just I'll just introduce you to what power is. Tomorrow we do problems that will actually like expand on the topic, and I will be able to explain it better. So what is power? One important concept that is related to energy being wasted or used is the concept of how much time it takes. And that is power. Power is rate of doing work or converting energy. So the more energy you convert in less time, the higher the power. So power is defined. So you remember this triangle, it means this definition. It is the work done divided by the time taken to do that. It is also equal to the change in energy, whatever change happened. Remember, this is not just energy, it is the change in energy divided by the time that it took to do that. And that is power. We will talk about this in detail tomorrow, and we will also solve some problems. If you have any questions, the floor is open. Good concerns raised by Maheen here that first of all, the sun will die out. Yeah, definitely. Sun will definitely die out. Sun, I think, has the best estimate to get through the, like, to estimate where the sun is in its life cycle would be to say it is halfway there. So I think that sun is going to die out. I don't know, maybe in a few million years or a few 100 million years. It's not really a conspiracy, it's actually true. Yeah, I think sun's age is right now. It's 4.5 billion years. So I guess itna hi aur chal jayega. थोड़ा सा आगे, थोड़ा सा और. Okay, why not save petrol and use public transport or a cycle or your feet? Yeah, there actually isn't something wrong with using petrol, but the problem is that what petrol is doing is it's using the sunlight that is given to us, that was given to the earth millions of years ago. And when you actually walk or you use a cycle, then what you're doing is you're using the sunlight that was actually more recent, like more fresh sunlight. If you were to say that it was the sunlight given to you that day or a few days ago, jab aapka khana prepare hua and all that. So there's nothing wrong with using that sunlight that we have, the fresh sunlight that we have. But the problem is when we take the ancient sunlight and release it into the atmosphere, and that is something that disturbs the ecological cycle of the planet. So it's important to control that. Conservation of energy, going more green, all of those things, all of those actions actually lead to a more sustainable world. But unfortunately, as you might have seen, the accident in I don't know, Gulf of Mexico these days, the one on a Pemex facility, those kind of accidents, they wreak havoc on the environment, and they're all because of this greed that humans have of, what do you say, development ke naam pe. We are exploiting resources without being responsible for the aftermath. So it's important to use the energy that we have, but also important to make sure कि उसका long-term harmful effects कम से कम हो. Public transport, whether it is better for the environment, that depends what kind of public transport is. Because, for example, if you're using an electric train, then it does not mean that you have reduced your carbon footprint or the impact on the environment. It is just that that's hidden from you. जब आप गाड़ी चलाते हो, you can actually see the smoke that's coming out of your car. Okay, don't look back when you're driving, but still you can technically see that. But the environmental effect of the electricity that runs that train, it's just hidden from you. It's more further away from you. So there are layers of secrecy there or privacy there. So you can't really see कि उसका impact क्या है. But what if that train is running on electricity that was produced using a really bad quality of coal? And that would mean that no wonder China is responsible for, I don't know, just the coal power production plants in China, they're responsible for around 15% or 17% of the global pollution because of this, just that coal power plant in China that we have. So yeah, it needs, whatever means you're using, whether it's public transport or not, it's important to understand कि उसका impact क्या है. Okay, so that's about it.